In this module, I'm going to begin our discussion for theory. So let's begin with what is a set. Now this is one of the concepts that we don't really define very formally, but informally this is what we are going to say. A set is an unordered collection of objects. These objects we are going to call elements or members of the set, and a set is called to contain its elements. A couple things. A set is an unordered collection. It's important, the order doesn't matter, and it's a collection of objects. The number of objects could be 0, the number of objects could be 1, 2, 5, 1,397,000, infinite, etc. Note that the definition of a set does not require that there be any relation among members of a set. So you can have a set containing a cat, dog, and number 5. It's perfectly okay. In a set, repeated elements are ignored. So it's a collection. So if I have some number repeated 5 times, we just count it once. To indicate the fact that X is an element of a set, we write this: X belongs to S. To say that X is not an element of S, we write X belongs to S and then we cross it out. So how do we describe a set? Now we can list all members of a set when it's possible. So if the set contained 5 elements, I could just list them. If the set contained 1,397,000 elements, I probably can't list them, or it might take a while. When I want to list a set explicitly, we are going to use these curly braces, and we are going to list all the elements in it. This is something we do when the number of elements in a set is small. Another way is to represent the set using a set builder notation. In this method, we write what is the characteristics of all the elements in the set in a way that will uniquely describe what the set is. So for example, I can say set X is equal to nature of the member and what description I want. So I can say I want all numbers that happen to be even. So in that case, this part will say that I want numbers, this part will say that I want even. So this is an example of that. Here we have nature of the number that I want is positive integers, and the property I want about it is that the number be even. Here are some important sets, important in the sense that we will come across them many times. We have a set of natural numbers that includes 0. We have a set of integers that includes 0, positive integers, negative integers. We have set of positive integers G plus that include 1, 2, 3, 4 and so on. We have rationals of the form P divided by Q. P and Q are integers and Q is not 0. We have a set of real numbers. We say that sets are equal if and only if they contain exactly the same elements. That means if I have two sets, S and X, then everything that is in S is in X and everything that is in X is in S. Now we just studied propositional logic, so we can write it as for all S, if X is in S, this implies that X is in set X. Likewise, if it is in set X, then it is in set S. Some other special sets that we will talk about is universal set. A universal set is a set of all possible elements under consideration. So what is a universal set? Well, it depends on what context you are talking about. So if I'm talking about, say, numbers, then I might say the real number is my universal set. Or if I'm talking about, say, animals, then the universal set will contain all possible animals. Another kind of set is a null or empty set. You can represent this as two curly braces with nothing in it, or the special symbol phi that represents the empty set. Note that this notation is not the same as the empty set. This is a set that contains one element and, oh, by the way, this set, the element that is contained is the empty set. The element that is contained in it is the empty set. We can use Venn diagrams to describe a set. So here, let's say we are describing a set that contains the set 1, 3, 5. Generally, we draw sets using circles or ovals. We write the universal set generally in terms of this rectangle. This represents the set of all elements under consideration. We can define a subset of a set. So A is a subset of P if and only if every element in A is an element in B. Note that the notation that we are using here is subset or equal. That means it's possible that A is equal to B, or A is a strict subset of B. That means B has strictly something more. We can write this as a formula from chapter 1. So here for all x is in A implies x is in B. A is said to be a proper subset of P if and only if A is a subset of P but not equal to B. To show that two sets are equal, we can show that one is a subset of another. So if I show A is a subset of B, B is a subset of A, then that would imply that A is equal to B. By definition, the null set is a subset of all sets. So for any set S, phi is a subset of S. Every set is a subset of itself. That means for all S, S is a subset of S. Next, we'll define the notion of cardinality of a set. Cardinality of a set is the number of elements in that set. So let S be a set. If there are exactly n distinct elements in the set S, then we say that n is the cardinality of set S. We say that a set S is finite if this n is a finite number. We use this notation. The notation is vertical line, the name of the set, another vertical line to denote the cardinality of set. As I said earlier, a set could be finite or it could be infinite. So if a set is infinite, that means it has infinitely many elements. The next operation we want to talk about is power set of a set. So the definition is as follows. Given a set S, the power set of S, we write this as this function P of S is the set of all subsets of S. So this includes the empty set as well as the set S itself. So for example, if I take the set as 1, 2, 5, then the power set of it contains 8 different sets. We start with the empty set, then we have 3 singletons, then we have 3 sets with 2 elements each, and then we have one that has all 3 elements in the set. One observation we can make is if the cardinality of set S is n, then the cardinality of power of set is going to be 2 to the power n. Once again, we have reached the check before you go ahead slide. So in this video, we defined what sets are and different ways of specifying sets. That included explicit notation where we use the curly braces to describe what the set is. Also, we looked at the set builder notations that is useful for defining more complex sets. We defined commonly used sets such as N, Z, etc. One important thing I want to get across in this is the difference between subset and member of, and that is something I have seen students confuse between. So here is an example of this. Phi, the empty set, is a subset of the set containing 2, 3, 5, but it is not an element of that set. A little challenge for those who are interested. Try to prove that if a set S contains 5 elements, P of S has 2 to the power 5 elements. Now you could do this by enumeration, but what I'm asking you to do is figure out what's the basic principle because of which this statement is true, and therefore it will be true for all other sets as well.